All right, gang, Math 6610, more on estimation, confidence intervals. Um, Again, you might think that I'm kind of beating a dead horse and just going into too much detail here. I hope you don't think that because, again, I've taught 6610 now at least once or twice a year since 2012. And these are the things that I've found that students just struggle with. They can kind of go through the motions of creating a confidence interval, but I don't feel comfortable, I'm sorry, I don't feel confident that they actually know, the theory behind this. So that's the reason. Now, as you may expect, these things are super, super, super easy to find using R. So I've put the confidence intervals down that we created in previous videos. So if I wanted to create the first video, the 95% confidence interval for the GRE, what I could do in R is just use the z-test function. But before I use that, I'd have to install a package. So sometimes sorry, I can't type and speak. Sometimes to access certain code, we have to install a package. It's not in the core, the base package. So that's the case with this. I want to use the z.test function. It's not included in the the base package, so I'll need to come up and choose a I don't know, let's just go with Ohio. No reason other than that's where we are. It takes a little time. It should load some stuff. Shouldn't take too long. Then I need to access the library. Now notice in the install packages, I put this in quotations. When I access a library for BSDA, I do not. That's going to happen every single time. All right, so what I want to use now is I want to use the z.test function. I want to calculate for GRE. It's kind of an odd situation where we know the population standard deviation. More about that later. That typically isn't the case. And next thing I want to do is do the confidence level of 0.95. Forgot to attach data. Not good. So do the z-test and it'll work this time. So you can see that 576.92, 598.48 is the confidence interval that we constructed by hand and we get with R. That's good when that matches, right? And trust me, it turns out it doesn't always match, especially when we start doing more complex things like evaluating maybe sampling distributions from a z-distribution with a chi-square distribution. So it gets a little bit more complicated. Now, if I wanted to replicate the prop test, the percentage of those admitted, I would use the prop test. Now, this test doesn't need a library added or a package added because it uses the base core. But what I would have to do here, it's a little strange. I'm not able to just input the admit yet. Later on, I'm going to show you ways to do that. But from a straightforward z-test for categorical data, I have to find the counts. So the percentage of yeses here, or proportion of yeses here are 127 out of, you can probably do the mental arithmetic anyway, but out of 400. So if I'm going to do the prop test, I have to enter these numbers, 127 out of 400. And I want the confidence level equal to, I think we used 0.90, right? Yeah, we did. And then I need to do something that's not going to make a lot of sense, but I need to have the automatic correction set to false. I'll explain more about that. See what actually happens in the prop test. Even though we're using a z-test, there's an underlying calculations going on using the chi-square distribution. So I want to control for some things there. Otherwise, our confidence interval will not match up. So you can see here that, again, allowing for a little bit of rounding issues, 0.28 to 357, so pretty close. Again, appreciating that we have some rounding errors. Now, what really happens if we're really going to estimate in reality? If we're estimating an unknown mu, how likely is it that the population standard deviation is known? Well, let me get rid of this. I don't need this right now. The fact of the matter is it's very, very, very unlikely. But if the population standard deviation is known, we use the z-distribution. If the population standard deviation is not known, in other words, that statement is false, then we get into something called the t-distribution. And the t-distribution is much more reasonable than is the z-distribution. So let's say we want to estimate where the population standard deviation is unknown. Well, we're going to use what's called the t-distribution. And instead of the z-distribution, which is a function of its mean and standard deviation, the standardized distribution has mean 0, standard deviation 1. The t-distribution is a function of degrees of freedom. And it turns out that the degrees of freedom is very, very easy to find. It's just n minus 1. So in our case, n was 400. So obviously, our degrees of freedom would be 399. So if we're going to calculate the confidence interval for using the t-distribution, population standard deviation unknown, we still have our point estimate, but we have our t-critical, and we still have our standard error, which would be sigma over the square root of n, but if sigma is not known, it's obviously clear to us we can't use it. So we use the sample standard deviation instead of the population standard deviation. So to do this, we need to find the mean. We found that before, but let's just, sometimes you jump around on videos. So 587.7. The t-distribution, we need to dive into the QT function. So I have a 95% confidence interval from the same logic previously. I have 0.025 in the left tail. But now I don't put 0 and 1, I put the degrees of freedom, which is equal to 399. So it turns out, because we have such a large sample size, that the t-critical is very, very close to what the z-critical is. So I would put here negative 1.966. The standard deviation is 115.52. And we still have a sample size of 400. Now, if I can put that in my calculator and not do something really silly, so the left side I would get 576.34. And the right I would get 599.06. All right, so if you compare that to the to the confidence interval for the z-critical, Um, you'll notice that the margin of error is a little bit higher here. In other words, the interval is wider. Okay, and that makes sense because we know less about the population distribution from which we have drawn this sample and are trying to make an estimate. So it's a little wider. So the t distribution, the t interval will have a larger margin of error, or the confidence interval will have a large will be wider for the t distribution. Now to do this with R, I would just do what's called a t-test and GRE, and I would use the confidence level equal 0.95. And you'll see that 576.34, 599.06 matches up perfectly, as it should. It'd be kind of goofy if it didn't, right? Okay, so next thing, I'm not going to demonstrate z-test. I don't believe, because we just don't use them in research. But in making the connection from sampling distributions and central limit theorem to estimation, it's always nice to make that intermediate calculation using the z-critical, the z distribution. But typically, if we're going to estimate a population mean, we will use the t distribution because our population standard deviation is typically unknown. All right, gang, all I got. We'll dive into hypothesis testing in the next video.